Hey guys, Miss Gosling here. In this video, you're going to be learning about simple harmonic motion. By the end of the video, you'll be able to define simple harmonic motion and apply the principles of simple harmonic motion to the mass pendulum and mass spring systems. So that's a lot, so let's go ahead and get right into things. So let's start by talking about something called periodic oscillations. And we're going to define periodic motion as any motion around a center with an equilibrium position. Simple harmonic motion, which we're going to get into pretty quickly, is a subset of periodic oscillations. So one example of a periodic oscillation would be if I'm standing here and I am just periodically walking between 2 points. I am going back and forth around an equilibrium position. Now, this is not really what we're talking about when we get into simple harmonic motion and this unit, but I wanted to just make it very clear that periodic oscillations are a very general topic. Simple harmonic motion, however, is much more specific. So for something to be in simple harmonic motion, there needs to be a restoring force, and the magnitude of the restoring force must be proportional to the displacement of the body. So that's a lot of words, but essentially it means that there should be something bringing me back to my equilibrium position if I leave it. So there should be some force pulling me back to equilibrium, and that force must increase the farther away I get from my equilibrium position. So my force should be bigger up here on a pendulum, for example, than it would be down at the bottom here, because that force, again, is proportional to displacement. So one really good example of simple harmonic motion is the mass pendulum system. And this sounds complicated. It's not. It's just a mass hanging on a string moving back and forth. So for our mass pendulum system, our equilibrium position is going to be right at the center. And the force, the restoring force in this system, is gravity. And specifically, what we're interested in is the fact that not all of gravity. So when we think about our system, we have two forces acting on it. We have the tension force, which is directed upwards, and we have gravity, which is directed straight down. Now, our mass is not falling off of our pendulum string. So what that means is if we split up the force of gravity into its into different components, one component that is in the same dimension as the tension and one that is not, we can see that some of our gravity is that the y component, I'm going to call it the y component of my gravity, and I'm going to call this the y component of my gravity because it's kind of more down, really. So we can see that that has to equal our tension because our mass is not falling off of the string, which means that this component of our force is going to be the force that is our restoring force. So it's that component of the gravitational force that is perpendicular to the string. So what's important about this is that the magnitude of our mass and therefore our weight is going to be constant, but the tension force and thus the y component of our gravitational force is going to be dependent on the angle of our pendulum. So as our pendulum moves upwards, the x component here is going to increase. That restoring force will increase. And that's how we know that this pendulum is in simple harmonic motion, because the restoring force is increasing the farther we are from equilibrium. Whereas, as is I think pretty clear, when we look at our object in equilibrium, all of the gravitational force is in the same frame as the tension force, and therefore there is zero restoring force, and it's just the object's inertia that's keeping it moving on its path. So because of the way that the mass pendulum system is set up, because of the way that the restoring forces work, if we are looking at a simple pendulum, so a pendulum, and we're looking at a pendulum with a very small angle. So again, an angle that is between 0 degrees and about, I'm going to say 15 degrees. we can actually calculate the period of the pendulum knowing nothing but the planet that we are on, which is of course which will give us our acceleration due to gravity, and the length of our pendulum string. And as you can see, when the length of our pendulum string increases, the period of the pendulum also increases. And when I say period, I do want to be very specific about what that means. The period of the pendulum is going to be the time that it takes the pendulum to go from equilibrium through its full range of motion. So up to its highest point, over to its highest point in the opposite direction, and back to equilibrium. So the time taken for one full cycle is going to be our period. So let's go ahead and look at one more example of simple harmonic motion. And that is the mass spring system. So here we have a mass hanging on a spring, attached to a spring of spring constant K. Now, this mass is sitting on a frictionless surface. So we have no force acting on it except for the spring force. So if I take my mass and I condense it in, I am containing some potential energy in that spring. And the mass, when released, is going to bounce to its equilibrium position here, back out to a maximum position, and is going to, with no friction, continue bouncing forever. Now, we know that the force of a spring is given by negative kx. That is, the force of our spring is always going to be opposite the displacement of our mass. So this is very clearly simple harmonic motion because the force that is acting on our mass is the spring force, and that is by definition related to the displacement of my mass. And we can find the period of our mass spring system. So again, the time for our mass to go from equilibrium to being condensed to being at its maximum extension back to equilibrium. That time is our period. And we can find that by multiplying 2 pi times the mass of our block and divide that by our spring constant K. And just because I know y'all haven't seen spring constants for a while, the spring constant K is something that we use to talk about how springy the spring is. So if the spring is tighter, if it's harder to press, K will be larger. If it's easier to move, then K will be smaller. So guys, let's go ahead and talk takeaways, because I know this is a lot of information. So first of all, in simple harmonic motion, the force on an object is always proportional to and in the opposite direction from its displacement. And we call that the restoring force. And I'm going to go ahead and recommend those of you who want to get 5, 6, 7s on that IB exam, this is something you want to add to your flashcards. Restoring force and simple harmonic motion. 2 very simple things that you are going to want to have a very exact definition for. So that's our first takeaway. Second takeaway is that 2 examples of simple harmonic motion are a mass on a pendulum and a mass on a horizontal spring, because in both cases, the restoring force is directly proportional to the displacement of our object. And there you have it, guys. You have now learned about simple harmonic motion. Now it is your turn to solve a couple of problems on your own. Best of luck and happy solving.